All right, well, we'll pick up some of the curvilinear kinematics that we were working on in class. So we have a couple of kinematics questions and then a few kinetics questions. So at a given instant, the airplane has a certain speed that is given to you. It also has an acceleration. Now, down in the picture, you're shown the direction of the velocity and also the direction of the acceleration, which is going to be 75 degrees right there off the tangential direction. So again, we know that velocity can only be in the tangential direction, and it doesn't say anything about whether or not the speed is constant. All it says is at that instant we have a known speed. So what we're going to do is take the acceleration that we know, which is again 75 degrees. We're going to use normal tangential coordinates here. And so we put the tangential in the direction of movement, right, which would be in the direction shown, right, the direction of the velocity vector. Right, the normal is orthogonal to it, and it's in the direction of the change of the tangential. So if we look ahead, we see that the circular path, right, has the tangential changing sort of to the left. So basically the normal ends up going always to the middle of the circle. So we're going to take this acceleration vector and we're just going to do a little trig with it. So the normal direction would be 14 with a sine 75 degrees and giving us a value of 13.52 meters per second squared. In the tangential direction, it's going to be 14 times cosine 75 degrees, which is equal to 3.62 meters per second squared. And we can kind of see again with the coordinate system, right? We can see the larger component in the normal direction. So at least that makes pretty good sense. So again, now we want to think about acceleration, right, as having two pieces. Right? When we talk about curvilinear motion, it has both a change in magnitude component and also a change in direction component. And that ends up being the centripetal acceleration. So again, our equation looks like the normal is equal to v squared over rho. And if we just kind of shuffle that around, we get that rho is equal to v squared over the normal acceleration. And so all we do is just plug in those values. We've got 30 meters per second squared. The normal acceleration we calculated above is 13.52 meters per second squared. And so we end up finding that curve radius is 66.6 meters. So that was one of the pieces that was asked for. You asked for the radius of curvature of the path. That'd be a pretty challenging calculation using XY coordinates. We'll actually have an equation for it here in just a second, but we'll happily take our radius of curvature from a pretty straightforward calculation. Right, it also asks for the rate of increase of the plane's speed. Right, that is v dot, so I know that v dot is equal to the tangential acceleration, which has a value up above, so it's 3.62 meters per second squared. So the plane is both increasing speed and it's traveling on in a circular path. So we have acceleration both in the tangential direction and in the normal direction. All right, moving along to another kinematic example. We have a motorcycle traveling on a curve, and now you're told something, and I'll highlight it in red right there, at a constant speed. So that should jump out to us, right? That is going to mean that v dot is equal to 0 in this case. Determine his acceleration when located at point A, and neglect the size of the motorcycle and the rider, so we'll just assume that that particle is sitting right on that curve. That curve, you're given an equation for the curve here, so we've got something that's going to be, again, defined in an XY coordinate system. And what we're going to end up doing is we are going to put again, from a coordinate point of view, there's the tangential direction, right? And normal, or towards the middle, right, of the circular or curved path would be the normal direction. And so we've got an equation. This would be one, again, for your equation sheet that gives you the radius of curvature in terms of the function y. And so what we need are some derivatives here. So we've got our equation written right there for y. If I take the derivative with respect to x, I get minus 1 times 500x to the minus 2. If I take the derivative again, I end up getting 2 times 500x to the negative 3. And so if we look over here at our picture, right, we see that we're asked for information when x equals 100. That's where the motorcyclist is located. So all we're going to do is plug those numbers in right there. I end up getting minus 0.05 for dy dx, the slope. And I end up getting an equation. Plugging in, I get 0.001 for the second derivative of y with respect to x. So then I'm just going to go ahead and calculate the radius of curvature. So I'm just going to plug those values in there. I need to take minus 0.05, square it. And then I need to take to the 3/2 power. I'm going to divide by 0.001. And if I do that math, I end up getting 1,003.8 feet. So again, at that instant, you can kind of see as this thing moves, right? The really tight right here, we had ended up with a very small radius of curvature. But where we're located, we got a radius of curvature, again, of about 1,003.8 feet. So again, our acceleration is going to be broken up into two components, tangential and normal. The tangential is the time rate of change of the velocity. We're told it was constant. The velocity was constant, so v dot is equal to 0. For my acceleration then, I end up with just one term left over. And so I end up with the term 30 feet per second. The velocity squared divided by 1,003.8 feet. And if I do that, I end up with 0.897 feet per second squared. And again, that would be in the normal direction, is how we would define that vector. So I'm going to leave this one for class. We'll do it on Wednesday. But we end up with an automobile that's moving on a path that's straight, and then it starts to curve. And so the issue is that we need to find out whether or not that automobile, when we're asked for something at 18 seconds, we need to know at 18 seconds where that automobile is located. And so that's what we end up doing. And you can kind of follow the kinematics, and we end up finding out that it's on the curve. And then that obviously then lends it to doing a tangential normal analysis for the acceleration. But we will pick that one up as we start class on Wednesday.